Okay, comparing coefficients, and the question after this sort of deserves its own video, I think. Comparing coefficients, hopefully you're kind of familiar with that from chapter 1 when we did our algebraic fractions. Okay, you might remember I said that that's a quick way to turn, well, let's just say as a little bit of revision, to turn a situation where you had a product in the denominator to, you know, something over a plus something over b. Okay, so comparing coefficients is used for all sorts of other purposes as well. So comparing coefficients, there's a few situations you can do this in. If you have something like this, the idea is the x squareds on the left should be equal to all of the x squareds on the right, and the x's on the left should be equal to the x's on the right. And the numbers, they're like the x zeros, should be equal on the left to the right. So we can do the same with vectors. So here, if we compare the x squareds, there's 3 on the left, and on the right, there will be a lots. So that's where that came from. We can do the same here. So i's and j's and k's, you can compare coefficients of I, j, and k. So the i's on the left should be equal to the i's on the right. So I would do something like that. I colon, so on the left, there's a 3. No other ones. On the right, there is p. So that's an equation. Yeah. In fact, that's kind of just solved something, hasn't it? 3 equals p. Then you look at j. So there is p plus 2 on the left. On the right, for j, there is minus q. Well, you see that you can use these together. So you can use that result over there. So p equals 3. What's this? 5 equals minus q. So q is minus 5. Yeah. And the last one, k, you know, you can do the same sort of thing. So 120 equals 4pqr. Well, we've got that one. We've got that one. So you could find r. Yeah. So this is called comparing coefficients. You also did a little bit of comparing coefficients when you did chapter 7 trigonometry. Do you remember when you did the r sine alpha thing? And you said like, oh, what goes with the sine x on the left is equal to what goes with the sine x on the right. That was the same idea. You can compare coefficients with sine and cos as well. So you can compare it with x squared, x1, and constants. You can compare it with vectors. You can actually compare it with sine x and cos x, especially if you do further maths. That last one's kind of important. Okay, so we used that in this sort of geometric example in 3D. So a reminder, you had a question like this from before, and it said, prove that they bisect. The basic strategy is you talk about how to get from the origin to the intersection point using both of the different diagonal lines. Here, that would be the blue and the orange, because the idea is no matter if you go there really directly or indirectly, the i's and j's and k's and everything, or the a's and b's and c's in this question, they should be the same on both sides, because no matter how you express a vector from one place to another, it should have the same set of values. Okay, so we do this. We talk about the origin to the intersection point. And this is going to prove that they bisect each other, that they cut each other in half. It's going to show that that distance there, OH, is half of OE, and it will do the same for the orange one as well. So what is OH as a fraction of the most direct path? Because OE is that blue line. How would you get from O to E? You would do A plus B, look, B, so that's B. So A plus B plus C, that would take you from there. So O to H must be some fraction of OE. Okay, they're using the letter R here. If you want to use lambda and then mu, as you did before, that's also correct. So OH is some fraction of OE. What's the other path using the other line in the question? Well, you could go from O to B, and then you could do some fraction of B to G. That's another way that takes you from O to H. It's more indirect, but that's not a problem. So we could go from O to B, and then we could go along the orange line. We could go some fraction along the orange line. Different letter, because I don't know yet that the fractions are the same. That's what I'm trying to prove. Well, this is all well and good, but we want something to work with, something to compare. So now we're going to put the A's and the B's and the C's in the question. So OH, this one here, is the same as R, some fraction of OE, and this is some fraction of that. Yeah, okay, we're just repeating what we said. Let's put the A's, the B's, and the C's in. So OH, for this one here, it's going to become this, isn't it? Some fraction of A plus B plus C, because that's how you get from O to E. You use the defined vectors here, A, B, and C. That will get you there. So this is one root, okay? One root, let's call this the blue root. The other one we talked about, we said you can go from O to B first. Well, that's the same as B. So O to B has become just B. And then we do some fraction of the orange line. Well, what is the orange line? The orange line is minus B plus A plus C. You can do it another way, but you should end up with this. And it's some fraction of that. That was, what was that? That was BG. So some fraction of BG. So all of that together on the right-hand side, this is sort of the second root. This is the, let's call this the orange line root. It used that, and then it used the orange line. So the A's, whatever goes with the A's on the left, must be equal to whatever goes with the A's on the right. Same for the B's and the C's. So let's do that now. R goes with A on the left. What goes with A on the right? Just S, isn't it? What about B? Well, on the left it's R. On the right, it's a bit more complicated. Look, there's one B there. And then you're going to have minus SB. So you're going to have minus S. Okay. For C, I think you end up with the same as the first line. R equals S. So they're the same equation. But if you use these together and solve them simultaneously, what you'll do is you'll find out that R equals S, and they're actually both a half. And that's what you wanted, because R and S, they describe how much of the line, how much of the whole blue line you have to travel to get from the origin to the middle. In other words, that is the midway point of the blue line. And the same here, half of the whole line, so that must be the midpoint of the orange line. So you prove they bisect each other because it's cut into two if it's halfway. Okay, very difficult looking question on the outside, but when you do a few of these, okay, you can learn them and you can really pick up quite a lot of marks on these questions. So definitely not something to shy away from. So pause the video and have a go at this one here. Looks a bit more difficult because there's fractions. My advice is use a quarter, 2 quarters, 1 quarter. And don't be put off by the fact that the line starts in. The technique is still the same. I'd like you to find some path. And then I'd like you to find another path using the other line. Those are just 2 suggestions that I'm sort of alluding to on the board. 10 marks if you can sort of follow along with the same techniques. Okay, that there is the mark scheme. So make sure you've had a good go at this one here, and the mark scheme for you to have a look over there. This one is also a half as well, but it doesn't always have to be a half. And you're ready now to have a go at 12C.